Have you ever stopped to wonder how your computer can stream music, download a huge file, and let you browse the web all at the exact same time without just, completely exploding? Well, there's this unseen battle happening inside it every single second, a constant negotiation for resources. Today, we're going to pull back the curtain on process synchronization and deadlocks. This is the hidden logic that keeps our entire digital world from collapsing into total chaos. All right, let's get into it.
Okay, think way, way back. What's the #1 rule of sharing you ever learned as a kid? It was probably something simple, right? Like take turns or one at a time. It's the basic rule that stops fights over a toy, or, more importantly, the last cookie. Well, it turns out that exact same principle is what's stopping your computer from basically tearing itself apart from the inside. You see, inside your phone or your laptop, you don't just have one program running. You've got thousands of little processes, and they're all scrambling, all competing for the same limited stuff. We're talking memory, CPU time, access to a file. This whole thing is called concurrency. And just like two kids trying to grab the same toy at the same time, if you don't have rules, you get absolute chaos.
So what does this digital chaos actually look like? Well, it leads to something that gives programmers nightmares. It's called a race condition, and it's one of those weird races where pretty much everybody can lose.
Let's paint a picture here. Imagine you and your partner share a bank account, and it's got a nice, even $1,000 in it. Now, at the exact same millisecond, you log in to deposit $200 and your partner logs in to withdraw $50. Both of these requests hit the bank's server at literally the same time.
And here is where everything goes wrong. The computer process for your deposit reads the balance, $1,000. At the same instant, the withdrawal process also reads the balance, $1,000. So your process does the math and calculates a new total of $1,200, and your partner's process calculates its new total of $950. The crazy part? Based on the information they had, they're both right.
So which balance actually gets saved to the account? In a race condition like this, the outcome is completely up for grabs. It all comes down to which process finishes its job and saves the result last. It is a frantic, messy race to the finish line.
And in our little story, let's say the withdrawal process was just a millisecond slower, so it finished last. The final balance in the account is now $950. Your $200 deposit? Poof, it's just gone. Vanished. It was overwritten and completely lost in the chaos. This right here is the reason an online store might accidentally sell you an item that's already out of stock, or why you get that frustrating lag spike in an online game.
So how on earth do we stop this from happening? Well, we do the same thing we do in the real world. We make some clear, non-negotiable rules for sharing.
In the world of programming, that little piece of code that touches a shared resource, like our bank account balance, has a special name. It's called the critical section. You should think of it like a highly sensitive room that only one person can be in at a time. The entire goal of process synchronization is just to create a polite, orderly system for entering and exiting this room.
Now, any good solution, any good system of rules has to satisfy three main requirements. These are the three pillars of keeping things in line: mutual exclusion, progress, and bounded waiting. We're going to focus on the big one first, the most important one.
And that big one is called mutual exclusion. And honestly, it's super simple. If one process is currently inside that critical section, no other process can get in. Period. End of story. So if your deposit process gets in first, the withdrawal process simply has to wait its turn outside. The other two rules, progress and bounded waiting, are there to make sure the line keeps moving and nobody has to wait forever. But mutual exclusion, that's the fundamental lock on the door.
Okay, so to actually enforce these rules, programmers don't just cross their fingers and hope for the best. They have a whole toolkit of special mechanisms designed specifically to manage who gets into these critical sections and when. Probably the most common tool in that kit is something called a Mutex lock. And the best analogy for it, by far, is the key to a single occupancy restroom. It's simple. Before a process can enter the critical section, it has to get the key, or in programming terms, acquire the lock. While it's holding that key, no other process can get in. Once it's done, it gives the key back. It releases the lock, allowing the next process in line to grab it.
Now, a slightly more advanced tool is called the semaphore, and it really comes in two flavors. First, you've got a binary semaphore, which honestly works almost exactly like that mutex lock we just talked about. It's basically an on-off switch. It's either available or it's not. But then you have the counting semaphore, and this one's a bit more powerful. Imagine you have, say, 5 printers available on a network. The semaphore's count would be set to 5. Every time a computer wants to print, it takes a key and the count goes down to 4. When it's done, it puts the key back and the count goes back up to 5. Pretty clever, right?
So we've got locks, we've got keys, we've brought order to the chaos. Problem solved, right? Well, not so fast. These very solutions, the tools we created to fix one problem, can actually create a brand new, even scarier problem, a complete system freeze known as the deadly embrace.
This is a deadlock. Just picture this. Process A has locked down resource 1, and it's waiting to get resource 2. But at the exact same time, Process B has locked down resource 2, and it's waiting for resource 1. See the problem? Neither one can move forward. They are stuck in a digital standoff, waiting for each other. Forever. This isn't just a bit of lag. This is the reason your entire application might freeze up solid, becoming completely unresponsive.
Now, for a deadlock to actually happen, it's not random. 4 very specific things have to be true at the exact same time. First, mutual exclusion, that one-at-a-time rule. Second, hold and wait, where a process holds one thing while waiting for another. Third, no preemption, meaning you can't just forcibly take a resource away from a process. And finally, circular wait, that standoff loop we just described. Now here's the crucial part. A deadlock can only happen if all 4 of these are true. If you can find a way to break just one of them, the deadlock can't happen.
So, since we know the 4 ingredients in the recipe for a deadlock, we can actually come up with some pretty clever strategies to either stop them from ever happening in the first place or to break them apart once they do.
When it comes to handling deadlocks, engineers usually follow one of 3 main philosophies. The first 2 are proactive, meaning they try to stop the problem before it starts. Prevention is all about designing the system in a way that makes one of those 4 conditions impossible. Avoidance is a bit smarter. It uses algorithms to look at every request for a resource and only says yes if it knows the system will stay in a safe state. And finally, you've got the reactive approach, detection and recovery. This one basically says, you know what, let deadlocks happen, we'll just have a system in place to find them and a plan to fix them.
And what does that recovery look like? Well, it's often not very pretty. It can mean just killing one of the stuck processes, just shutting it down, or forcibly ripping a resource away from it. In fact, anytime your computer freezes and you have to force quit an application or just restart the whole machine, you are, in a way, manually performing deadlock recovery. You're breaking the cycle.
All of this brings us to a final, much bigger question. Because these aren't just abstract problems for computer science students. These are the things that govern financial trading systems, our power grids, networks of self-driving cars. So as we build this incredibly complex and interconnected world, are we engineering systems that are truly safe from the ultimate digital gridlock? What happens when the whole system gets stuck in a deadly embrace? It's definitely something to think about.